Okay, thank you. Okay. Hello and good afternoon to the third live session on model predictive control course. Okay. So first off, yes. So before we start, just a quick note. Um a whole lot of MPC that or model predictive control applications that you see in research today, or for that matter in the industry today, they use pre-packaged softwares. So, for example, MATLAB has MPC toolbox. Most of the automation companies have their own internal MPC implementations. Not just MATLAB, there are MPC equivalent of MPC toolbox available on some other platforms as well. Uh, so a whole lot of MPC work that is done using these toolboxes. So you kind of have to give the models. You have to define, what's your parameters. You have to define your horizons. You have to define whether you need an estimator or not. You have to define what your outputs are, what are the controlled outputs, what are the measured outputs, what are the unmeasured components, what are disturbances. All those things you need to define. And once you do that, the box, the MPC box, the black box, if you can call it that, calculates everything for you. You can implement that on an actual system or a model system, and that runs. That's how, for the most part, MPC is used now. Now, what we have done in week number 5 and 6 is we have gone under the hood and tried to do the actual coding for MPC. I have restricted just to CISO MPC for now, but literally there's really nothing there in CISO MPC that needs to be changed when you go to MIMO MPC, other than the fact that how you construct your S matrix. Once you get the construction of the the SU and the big SU matrices right, there's nothing else that really needs to be different. So although we have done this for CISO, it's very well extendable to MIMO as well. The only difference in CISO is that we were going from 1 to end minus 1. Instead, we will go to 1 to end minus ny. That's the only difference that will happen. And to get y, we are not extracting just the first element, but we are extracting first and y elements. Other than that, it's exactly the same. However, coding gets a little bit complex, and although in the in-person class that I teach in IIT Madras, I do MIMO. But last semester, because we had to do the class remotely because of the COVID situation, I realized that in the absence of face-to-face interaction, MIMO becomes a little bit confusing to handle, whereas CISO does not become that confusing. So that's why I have stuck to CISO. Coming back to this, what I wanted to say is that, for example, you have signed up for a class where you want to learn how to drive a car and how to appreciate driving a car. And week number 5 and 6, what I'm going to trying to tell you is a part of appreciating the car is also opening the bonnet of the car, seeing the engine, seeing this is where the goes, oil filter goes, this is where the radiator is, and maybe even change the oil, change the radiator fluid and all that. That's something that is different than just simple driving of the car. So therefore, week number 5 and 6 are probably tougher than any other week in this course. Week number 1, 2, 3, 4 were about concepts. Week number 7 is going to be about concepts. 7, 8, 8 and 9 would be partly concepts, partly implementation. 10, 11, 12 will be about implementation. 5 and 6 is about the core coding, the nuts and bolts, the engine of the MPC, and therefore week number 5 and 6 are going to be a little bit tougher. Yeah, if you do struggle, let us know, and we'll try to help you out. But usually week seven becomes quite significantly more streamlined and a little bit easier than week number 5 and 6. So that is one thing that I kind of wanted to state to you. So do expect this week to be a little bit tough. Uh, so a few, not a few, at least one of you have asked that uh, the video for making the MPC code was incomplete. So what's happened is that the second part of the video, it's kind of lost somewhere. I'm not sure where it's lost, in the sense that I did that recording in the studio, and last 15 minutes I recorded it on my laptop, uh, and I'm unable to find that on the laptop. So however, that was not an hindrance to using MPC codes. Why? Is because that entire code is made available to you. So, not being able to see the video is not going to be the hindrance for doing the assignment. Yes, it might be a little bit of a hindrance for understanding the coding of MPC, not implementation of MPC. And I'll try to re-record the videos. I do very much realized that I had made a promise of recording something for you in week number 4 in the previous live session, and I probably did only 80% of that, and I kind of got very busy and could not complete it for various things that occupied my time. But again, this is something that I'll definitely do it before the course ends. Let me see if I can do it in either this weekend or the next weekend. What I'm talking about is re-recording the rest of the video where I'm doing the coding for MPC using step response models. So I'll try to do that. There was a request that whether or not the assignment solutions, whether I can do a video of them and put them online. The coding solutions, maybe I'll try to do some video that might be a little bit helpful. In my other MATLAB course, doing things on the video has definitely been helpful. Again, I can't promise timelines because I'm running two courses on NPTEL as well as courses in IIT Madras. Have PhD students who are working with me that require my attention. So I cannot promise, but I'll try to do my best that at least before the full course ends, you will have these videos. But I'll try to do them earlier if possible. Okay. Now, with that, let me come to the the questions. Sorry. Okay. What is feedback control? Feedback control basically means that this is your process. Then you have your sensors. These are your Y measured. This is your controller. Okay. And maybe this is your set point. Okay, this is the kind of structure that we have basically seen over here. Now, what did we do in PI controllers, PID controllers? Okay, we looked at Y set point minus Y measured. This we defined it as error, and then we said U is going to be proportional to the error plus integral of the error plus derivative of the error. And again, although whatever I've written is right, but I'm kind of doing it in a very pedagogically simple way, not necessarily in a rigorous way. Okay, this was what we talked about with PID. As far as PID is concerned, whatever information that you gain from doing the measurements, that is complete. That is not how any of the advanced controllers work. Nearly every advanced controller requires you to obtain the state of the system. What do you mean by the state of the system? State of the system means internal representation of the system that would be necessary in order to predict the system behavior, or that would be necessary to control the system behavior, or analyze the system behavior, or monitor the system behavior, or ensure that the system is working in a safe mode. Okay, so you have safety requirements, you have quality requirements, you have economic requirements, you have overall monitoring and health and monitoring requirements, and at different levels you require all these requirements to be met. That's a very different paradigm than PI PID controller. Okay, that is the advanced level. PI PID come at what is known as the regulatory level of control. Okay, so for advanced level of control, what we need is from the outputs, you need to estimate the states, and that is known, what we put over there is known as observer or estimator. Okay, so the observer takes in the outputs as also the inputs, and based on that it gives you the estimate of states x hat. Okay, so from ym and u, it is going to give us x. That is what an observer means. Now, example. I had given this example in the first week video. Let's say you are driving a vehicle. Okay, and let's say there is another vehicle in front of you, smaller vehicle that's that is in front of you, and you want to overtake that vehicle, right? What are you actually measuring? The measurement is your own velocity or my speed, and some idea, a qualitative idea of the distance between the person in front of us or front of me and myself. Okay, based on my knowledge of the velocity and how that distance is changing, I would kind of get an estimate of the velocity of the other person. Okay, now I decide that I'm going to overtake that person. As I'm overtaking the person, I'm not only keeping tab of the distance between the two vehicles, but I'm also keeping tab of how that distance changes. Okay, sometimes it has happened that we have decided that we are going to overtake the person, and that person has started speeding up. What do we do if there is a vehicle coming from the other side, for example, or if the road is curving? We say, okay, that person has accelerated, we'll just slow down and go back behind that person. Why do we do that? We don't do it based on my velocity and the distance between me and that person. We use the information about my velocity, the distance between us, and how that distance is changing in order to get a mental picture, a qualitative picture. Why qualitative picture? Because humans are qualitative animals. We are not quantitative animals or quantitative things like computers. So we kind of get an idea of what that person's velocity and acceleration is, what my velocity and acceleration is, and if my velocity is faster than the other person's velocity and my accelerate, and that person is not started accelerating, I decide, okay, it is safe to overtake. If that person is accelerating, I say that, okay, it's not worth overtaking, I'll go back and uh, come back behind that particular person. So what are we using in order to make the control decisions? We are not using ym only. Using ym, using our velocity and the distance and time between the car in front of us and us, we are estimating all other information. We are estimating the other car's velocity, we are estimating the other car's acceleration, we are estimating our own acceleration, and based on this the decision is being taken whether or not I will overtake the car. The decision of overtaking the car has no set point. Okay, set point was a concept that comes really from regulatory control. Okay, so what was the control objective? The control objective was to safely pass the car. What does that mean? That means that my location relative to the car's location is I'm going to be in front of the car, which you can express it mathematically using the coordinate system. You can, this is x coordinate, this is y coordinate, this is z coordinate. We're not flying, so forget the z coordinate. What I'm saying is that after some amount of time, my x coordinate should be greater than the x coordinate of this car. Okay, that is going to be my control objective. That's got nothing to do with set point. If it was set point, what that would mean is bam, I'll go and bang the car. That's not the aim, right? So the concepts of pi controller are different or much more limiting than the concept of advanced process control. MPC comes under the advanced process control level. Likewise, MPC is not the only algorithm. Of course, you have adaptive control, model reference adaptive control, sliding mode control, ratio control, all of those, and optimal control theories, reinforcement learning based control. All of them come under either advanced process control or even higher levels in some cases. So there was a question that said that can you explain MPC in the context of PI/PID? Unfortunately, there isn't a direct one-to-one relationship between MPC and a PI/PID. So sorry, that is not really possible to do because it's a very different concept than PI/PID concept. The next question was, or first question was, what is Kalman filter? How is it different than MPC? Okay, this is where Kalman filter can be used. Okay, Kalman filter is not the only algorithm that can be used. There are other algorithms also. Kalman filter is one of the more popular recursive algorithm that can be used as an observer. This is where MPC can be used. Again, as I said, MPC is not the only algorithm that can be used over here. There are other algorithms as well. Okay, so what does Kalman filter does? Takes measured variables, takes the input information, and generates the state information. What MPC or any controller does is takes X hat information, okay, takes set point or an objective function, and computes the manipulated input. So that's the difference between Kalman filter and MPC. Okay, MPC, because it is predictive in nature, there is not just feedback component, there's also feed forward component. What do we mean by feed forward component? Let's say, for example, you're looking at shower, your bathroom shower. There's a shower heater, and some of the real fancy heaters or something like that, they have this temperature controller where you can set the temperature at say 39, 40, 41 degrees Celsius. Okay, and then there is a controller that determines that. Okay, let us say, for example, that over the half an hour period that heater was being used, because people were taking shower at various rooms in a hotel. Let's say that heater was being used over the period of 1 hour. It went from cloudy skies to really bright and sunny. So outside temperature increased from, let's say, 20 degrees Celsius to 25 degrees Celsius. In feedback control, you need to wait for the effect of that 25 degrees Celsius to be felt on the output measured variables before the input can make any corrective actions. MPC has a feed forward component. You can use the measured disturbance, and you can predict using measured disturbance what the effect of measured disturbance in the future would be, and therefore take corrective actions a priori. That is similar to the feed forward control concept that you would have studied in your undergraduate. Okay, so MPC, I usually don't directly call it a feed forward or a feedback controller, because the idea is a little bit broader when we talk about MPC. But MPC is a controller that has the ability to take feed forward actions, that has the ability to do feedback corrections as well. Okay, that's the versatility of MPC. Coming back to the first question, MPC versus PID. I know you did not ask this question in the context of versus PID, but I have just rephrased it. So, okay, this is known as what is known as a control hierarchy. The lowest level is known as the regulatory control. The next level is known as advanced process control. The next level is known as real-time optimizer. Okay. Next level is known as planning and scheduling. Okay, and next level is known as strategic decisions. This one is taken at the level of each individual control loop. This one does not work usually at the level of a control loop, but it usually works at the level of a unit or multiple units. RTO works at the level of subplants or multi-units. Planning and scheduling works at the entire plant. And strategic decisions work at the level of entire enterprise. Okay, so let's go from top to bottom. Let's take an example of, let's say, Jamnagar petrochemical factory. Enterprise level would be the multiple petrochemical factories that Reliance owns. Plant level would be the Jamnagar petrochemical factory, or maybe, let's say, for example, one particular product that factory makes. RTO level would be at the level of one particular section in that particular plant. APC level would be at the level of reactor, separator, storage units, cooler, heaters, all of that level. Regulatory control will be level at the level of each and every control loop. Okay. APC level is where model predictive controller works. This works at regulatory control level. Okay, so therefore, I cannot really express APC in terms of a control law like PI control law or PID control law. Please explain the derivation of G11, G21, G22 for tutorial part 1 for MIMO system. Okay, so let's say, again, I don't remember exactly what that was, but let's say this was e to the power minus 5s. There was no e there, no time delay. So let's see, divided by 36 square, 12s plus 1. Okay, so this you can convert it into state space format. And there are different ways to do that. The one that I will suggest is what is known as controllable canonical form. Okay, so this will give us x dot equal to ACX plus BCU, y equal to CCX. Okay, and you can look that up, what that controllable canonical form is, and you'll be very easily be able to put this particular this thing into the controllable canonical form. After that, you can do discretization. Okay, how to do discretization? You'll get basically xk plus 1 equal to AXK plus give BUK YK equal to CXK, right? Where A is nothing but e to the power AC multiplied by H, where H is the sampling interval, right? So we have done that in the class. Okay, this is if you wanted to do this using uh, hand calculations, something of the nature that might be required in the exam. If you are using MATLAB, you will use ss command in order to get this. In order to get this, you will use tf command. Okay, and maybe I'll you'll use MATLAB ss command to get G11 in, and I will use MATLAB C2D command to get it in. Okay, so you can use either of these techniques in order to get that. Okay, okay. Can you please share MATLAB or Simulink implementation of MPC for any application like buck converter? I'm not able to use it. Okay, so if you are looking at general understanding of MPC, that is what is being done in week number 6. So there was a question: can I give you a MATLAB implementation of MPC? If you're talking about you wanting to use it for certain applications, let's say either in your research or in your work, we are going to use MATLAB toolbox for MPC. We will use that in week number 11 and 12. Okay, that is when you will get the answer to your question that hey, I wanted to learn MPC to use the MPC MATLABs or Simulink MPC boxes in order to solve the problem of my interest. Yes, that is indeed a major aim of this course, but I do not want to just tell you this is MATLAB toolbox, go use it, do this, do this, do this. No, what I intend to do is talk about the basics in weeks number 1 to 4, talk about under the hood of how MPC works, but using a using a step response MPC. Then week number 7, 8, 9, I'm going to talk about at week number 7, 8, 9, 10. I'm going to talk about linear time invariant models and linear quadratic control and estimation. That becomes a very important theoretical underpinning for MPC. And last 2 weeks, we will take up problems which would be of a little bit more practical nature using MPC toolbox. So that is the overall idea behind this course. So week number 1 and 2 were math background. Week number 3 and 4 were modeling background. Week number 5 and 6, code your step response MPC or DMC. Week number 7, 8, 9, 10 is linear control theory. Week number 11 and 12 MPC. Okay, so yes, we'll take this up when we come to this. Simplified MPC, in my personal opinion, is not even MPC. They've just used the term, MPC as it was popular over there. Okay, the concept of MPC has always been quite specific. So the question was that in early 90s, simplified MPC was derived from internal model control. So simplified MPC is basically concepts from internal model control and the concepts from uh, uh, adaptive control theory. They have in order to kind of make some modifications, they use certain receding horizon type concepts from MPC literature. Okay. Today, when people talk about simplified MPC is spoken about in two different two more concepts contexts. The other context that simplified MPC is used for is how to make easy the process of tuning the MPC parameters and how to get the model in a simplified way. The other context in which simplified MPC is used is MPC takes a lot of time, simulation time to run. So how can we reduce the simulation time by using certain amount of strategies? So for example, if you are doing, for example, non-linear MPC, it might take seconds to minutes in order to give one single control action. Whereas if the faster MPC work in the time scale of 0.1 to 1 second. For electrical mechanical system, that might be too slow. So, or for embedded process, that might be too slow. So how can you adapt the MPC to apply it to faster processes and to applications such as embedded process control, so that MPC can be run on a microchip itself rather than a full-fledged computer. So that's the other context in which the term simplified MPC is also used. The context in which you have used the term simplified MPC is more related to IMC, internal model control, than to the MPC algorithm itself. Okay, so yeah, so I think these were the questions that came up before this session. Let me see what questions are there, if any, on the live session. Yeah, in week 5, we were asked to give Hessian value. How can you do it in MATLAB? Actually, I don't remember exactly the question, but uh, yeah, the definition of Hessian. Okay, so let us say our S was say 1, 0 0.5, 0 0.25, 0 0.125, 0 0.0625, and so on. Okay, let's say we have P equal to 4, M equal to 2. Okay, prediction horizon is 4, control horizon is 2. Then our big SU, how is that going to look like? It will be 1, 0 0.5, 0 0.25, 0 0.125, 0, 1, 0 0.5, 0 0.25. Okay, let's say our gamma y, our q is going to be equal to let's say 4. Okay, and let's say our r is going to be 0 0.5. Okay, in which case gamma y is going to be a 4 by 4 matrix where diagonal elements are 4. This is going to be our gamma y, gamma u. Okay, can just substitute this guy over here, substitute this guy over here. Substitute this guy over here. That's your Hessian. Okay, can do it with hand calculations. If P and M are small, if P and M are large, you'll need to do MATLAB based calculations. You can even do it in Excel. You can do it in any kind of way that you find fit. So yeah, it's the concept is not difficult. Coding may be a little bit involved, but conceptually it's quite straightforward. Okay. I want to learn how to use MATLAB for process control using basics. I need a little more information about what you mean by that. Yeah, Harish, Arunagiri Harish, if you give more information, I might be able to give a little bit more help. Uh, uh, Now, it really depends, what your aim is. If you're talking, and again it depends on what your field is. If it is in chemical engineering, mechanical engineering, the suggestions would be different. If you're looking at computer based control, then by Astrom and Wittenmark. If you're done generally talking about linear control systems, then linear control theory by Thomas Kailath. If you are talking about model predictive control, by Camacho, Eduardo Camacho, or by I'm blanking out on the name. Now, if you want a theoretical treatment of MPC, then you can look at Main and Rawlings. If you want a hybrid MPC treatment, Bemporad and co-workers. So these are the various books. Now, if you're talking about you want to really understand the MATLAB implementation, the things that are covered in these two books will be covered using Control System Toolbox. This is also covered in MPC Toolbox as well as Optimization Toolbox. Alberto Bemporad is the author or one of the authors of MPC Toolbox. Okay, so yeah, his material would also be useful. Now, why I'm talking about the toolboxes is each of the toolbox or most of the toolbox have solved examples or tutorial examples in their user guides. In fact, in week number 11, I'm going to take one example from MATLAB's user guide itself, and I will go over that particular example so that you can then look at the user guide and expand beyond what just I have discussed in week number 11. These user guides are very useful places to talk about how to do MATLAB based implementation. So hopefully this answered your question. I'm not fully sure if that was essentially what your question was. Pooja's question: how does MPC stabilize an unstable plant? The whole concept about stabilizing an unstable plant, or for that matter, stabilizing a stable or keeping a stable system stable, is to ensure that the closed loop poles of the system are within the unit disk. Closed loop pole for discrete time system are in the unit disk is equivalent to saying for continuous time system the closed loop poles are to the left half plane. Okay, now how do we ensure that? uh, how about this is let's go over the material that we are going to cover in week number 7 and 8. 7, 8 and 10. Week number 10 takes material from 8 and 9, so let's go over the material from 7, 8, 9 and 10. In week 10 we will have one more live session, so not the next live session, the live session after that. By then you would have finished your week 9's assignment also. uh, Hopefully there will be a little bit more clarity about various things that will help me tackle this particular question. So please come back and ask me this question at that point of time, and I'll be happy to answer. Yes, there are theoretical ways in order to look at how can we ensure stability or not. I want to learn control systems theory for autonomous robots. How to go about doing it? Learn the control theory, learn robotics, and then try to combine both. So that's the way to go about it. This particular course will cover the control theoretic part of it. You may want to look into an equivalent robotics course and go ahead and try to implement the tools that you have learned over here onto that particular system. You'll probably need to extend yourself a little bit. You may with the hybrid systems work that I talked about with Bemporad's work, Alberto Bemporad's work, that might be something that to look into. There would be an example or two in the MPC user guide that talks about control of hybrid systems, and that you can extend to robotics as well. Hand calculations for each. Okay, next question. Assignment 3, problem 3, step response coefficient for MIMO. I don't think I would have asked you MIMO to do by hand, right? Yeah, of course, MIMO by hand is going to take a lot of time. I mean, unfortunately, uh, the way we have to teach control, we kind of have to teach CISO first. We have to teach the uh, transfer function based approach first, because those are the base level concepts, and only after that we can build APC. Last year there were students who did my in IIT Madras who did my MPC course before they had done their undergraduate base level process control course. And one of them actually asked, I mean, why do we even need base level process control for MPC? Because the concepts are very different. We require base level. So we saw that pyramid, right? So if I teach you MPC before I teach you regulatory control, I'm basically building up first floor without having ground floor at all. So that's why we always teach uh, regulatory control before we go on to advanced process control. But those are different concepts. Okay. Now, why am I bringing this up? Uh, if you ask me question like, okay, I have a 10 by 10 system and these are the 100 transfer functions. I would want to convert the transfer functions into step response coefficients. The question that I or a lot of people will ask is, why did you even convert them into transfer functions? Right? We don't naturally get transfer functions. We do first principles model, then take a Laplace transform, then convert it into transfer functions. We get the data from experiments and then identify the models as transfer functions. We get data and then try to fit transfer functions to either the frequency response data or to the time response data. The question is, why do we even need to fit the transfer functions if the aim is to do MPC? If I were to do that, I would have skipped the transfer function part. In industry, you skip the transfer function part when you're designing MPC. You directly get the step response coefficients or the state space models in MPC. So if the question is more generic, how if you have to do it for a large scale system, you actually don't have a choice, but you have to do it for G11 separately, G12 separately, G21 separately, G22 separately, right? So if you have G11 is equal to 1 divided by 5s plus 1, you convert it into again, which I just showed earlier. You convert it into state space model and then combine the state space model together if you want to get state space model. If you want to get transfer function model, you do 1 divided by s, 1 by 5s plus 1, Laplace inverse of this, split it into partial fractions, you get 1s matrix. Do that again for G12, do that again for G13, do that again for each of those 100 transfer functions, and then put all of these together. So if your question is, how do you do this? This is really the primary way that you do this. How do you do this in MATLAB? You create a transfer function G11, G12 up to G1, 100, G21, G22 up to G2, 100, and so on up to G100, 1, G100, 2 up to G100, 100, and then run a step response, generate step response coefficient using the command step, and then build your S matrix. So now, if the question is about MPC and what you should do when it comes to MPC, use MATLAB. If the question is about what you should do in order to do successfully in this course, use MATLAB as well as hand calculations. There is a significant value in hand calculations. We get a feel for how the algorithm behaves when we do those hand calculations. But the hand calculations, I will always do it for either a CISO system or two input single output system, one input two output system. I will not do it for a larger system. Reason is concepts are about those individual items. They are not about doing 550 multiplications and divisions and additions and subtractions in order to get one value so that you can get 2 points out of 100. That's not the aim. So when it comes to exam, don't worry about it. I'm going to restrict myself to 1 by 1, 1 by 2, or 2 by 1 system itself. When it comes to MATLAB, we are going to use larger systems, but not humongously large, maximum 2 by 2 or 3 by 3. Okay. Hopefully that answers your questions completely when it comes to what should I do in my work slash research versus what should I do for this particular course. For this particular course, do both. For work and research, you can stick to MATLAB, but there is a big value in doing a couple of small problems, CISO problems by hand. There's no transfer function of MPC, Pooja. Okay, there isn't a transfer function of for MPC. The biggest advantage of MPC is that the MPC is useful even for systems with constraints. Handling constraints makes the controller non-linear. If the controller is non-linear, there isn't a transfer function for a non-linear controller. Okay, so it's a different concept, it's a different way of doing things than um, uh, PI, PID, or for that matter, transfer function. Okay, so I mean, if you and that's the reason why I gave a long lecture about it's a different part of the pyramid. Why even bother with transfer functions in that part of the pyramid is what I would say. I want to implement MPC for my research work. So in the beginner level, where to start? This course, MPC. Yeah, this course, MPC toolbox is of course where you can start. I kind of don't mean it as a joke. I mean it seriously. Why? Where do we start? We start with one level before MPC also. We build up our concepts for linear models. We build up our concepts for linear control systems. We build up our concept for stability of the system, and then on top of that, we build our MPC concepts. Once you build those concepts, then you can go and look at MPC toolbox and try to utilize it. And that's exactly what this course does. 2 weeks of basic linear algebra and control system fundas, 2 weeks of modeling, 2 weeks of step response based MPC so that you get feel for how MPC works, 4 weeks of linear control theory, 2 weeks of MPC implementation. That should equip you to start reading the books. Which books? The books that I have just mentioned in the notes over here. These books and the user guides. Okay, that would be a good place to start. Okay, that would build up your fundas for using MPC. Then you can use MPC to solve the problem that you are going to that you intend to use for your MS or PhD or your any other research that you intend to use it for. No, Pramod's question, using TF function in MATLAB, how to display TF? Transfer function was the most convenient way for me to give you the problem statement. Uh, don't use TF in your assignment. Okay, this is what is already done in your assignment 6 first part, in the uploaded code. Okay, use the exact same concept. Build your SD. That's all. Nothing more than that. Okay, so this is the TF. You will give the step. We will call this equal to GD. We will call this equal to G. Okay, when you get your outputs, you can build your SD using the outputs. Okay, when it came to your getting your Hessian, you had to build your SU. That kind of an SU SD is not required to be built because that's not really used in MP, MPC calculations. So that's all there is to it. Okay, that's the only tricky problem in the entire course. Other problems are a little less trickier. I mean, it's not that they are simple, but this is the only tricky problem. So I will suggest that beyond this, just go and try to do a pattern matching in order to really understand what how you can address. So you have your component where you get your SU matrix. Repeat the same concepts, use pattern matching to repeat the same concepts to get your SD matrix. There's no capital SU concept for or big SU, sorry, big SD concept the way it is there in big SU. So you don't have to worry about that. Hessian calculation, SD is not used. You don't have to worry about that. SD is used only in gradient calculation. There's only a small change the way you use SD. That is what you would need to use, and that's really all that there is to it. So I don't know if I answered your question, but essentially that's the hint that is kind of provided in the PDF document as well. Okay. Yeah. So first term is indeed with the step signal. The second term is also with the step signal. As I had said a couple of times in past video lectures, measured disturbances are absolutely the same as manipulated input, except you cannot change the disturbance value. Nature changes it, right? So for example, ambient temperature, you can't change it. uh, the nature changes it. The example where I gave, you're overtaking the car, the vehicle, the speed of the car that you are trying to overtake, you don't do anything. It's that particular driver who is driving that car, that changes that value. So but as far as the modeling is concerned, D is treated in exact same way as U, except for one fact that you can change U, you cannot change D. D remains whatever value that you get. Yeah, so Pramod, it's really up to you. How do you want to do it? I would suggest yes. Upload the graphs. So put it all in PDF, and upload the graphs so that you can make a very cogent case for this. The other thing that I would want you to also focus on is how you will represent those graphs. So graphs, you will want to put Y as well as U. Maybe you will use subplot in order to get that. You might put the two graphs next to each other. How do you want to use the graphs in order to make your point? So think about that as well. If for example, you want to learn it for report writing, let's say, if you want to learn it only for learning MPC, fair enough, just copy paste the graphs one after the other. But most importantly, the statement that summarizes the observations that you made is the most important component. The graphs are primarily your evidence to say that this is the evidence based on which I'm making these conclusions. So that is what I would like to see. But most important part is not the graphs. The most important part is the conclusions that you draw by looking at the graphs. Okay, cool. All right, we are over time. So, any other questions? Okay. If not, then we'll come to the end of this session. And yeah, uh, just to actually clarify to most of you, right? I mean, I also did, for example, transfer functions and all that before I went on to MPC. So the kind of questions some of you had, if I remember back in the days when I myself was a student, I mean, I really had similar questions. How can we interpret in terms of transfer functions? What relation does it have to PI controller and all that? Over the years, I've learned to realize that these are basically kind of two different levels. The regulatory level is the grassroots workers and so on. The upper level is basically, okay, we try to organize everything and put those things together. The even upper level workers are basically, oh, how do we best improve the quality and the productivity, and even upper level worker, how do we maximize the profits? That's how it really works. That's where that's why this pyramid is there. Okay. Can you please explain MPC in a simplest way, what it's functioning? Okay. So, Pooja, if I may ask you, do you have a background in PI/PID controllers only, or do you also have a background in a linear quadratic control theory? That way, I'll be able to answer your question. This is for Pooja. Okay. If you can type out whether your background is PI controller, or you also have background in linear quadratic control theory, then accordingly I'll try to answer your question. Okay, only in PI. Okay, fine. Good. So I'll try to answer this. Okay, this is our set point. This is where our output is. Okay, our aim is to go to the set point. Okay, what does PI controller or PID controller do? It looks at the error. Okay, based on this error, it determines our input, so that from this point it would have gone over here. Okay, then it looks at the error again. Okay, and then it says that, okay, the integral of error was so and so. I can use these 2 points to determine the derivative of that error, which has the predictive ability. And based on that, we can say that, okay, there is some amount of error that is left behind. Okay, but we are not going to the set point fast enough, so maybe we can go a little bit like this, then maybe like this, then maybe like this, then maybe like this. Okay, this is what PI controller does. So PI controller, at every time instance, it is only taking in the outputs, comparing it with our set point, and determining what is going to be our next control action. Okay, what does MPC do? Okay, at this point, MPC is not at all going to look at the error. Okay, it does not look at this error at all. It says that if I make control actions like this is going to be my trajectory. If I make control actions like this is going to be my trajectory. If I make control actions like this is going to be my trajectory. Okay, then based on all these three, it says, you know what, this is the best way for me to do. Okay, so this is a very good trajectory for me to follow. So therefore, I will use this particular control move. Because I have used this control move, I will go from this point to, let's say, this particular point. I will repeat all of this all over again. Okay, so what does PID do? There is a chess game. Okay, you have your king over here, you have one particular this guy over here, let's say you have your queen over here, right? So let's say no pawn. Okay, let's say your opponent has a rook over here, and let's say uh, yeah rook over here, and let's say a queen over here. Okay, and let's say this person decides to sacrifice bishop. Your queen moves over here, does checkmate for you, lost the game. This is how PI controller works. How does MPC controller works? MPC says, if I move this queen and kill the bishop, this queen will come and take my pawn. I'm dead. I'm going to lose the game. Okay, I'm not going to move the queen. If I move this particular guy over here, oh, okay, I will put my opponent on the back foot. Then the opponent is going to make this move. Oh, then I will be in trouble. Maybe this is not the move that I should make. If I make move like this, then the opponent will move this move. Then I will make this move. Then opponent will make this move. Then I will make this move. Then opponent will make this move. Then I will make this move. Then opponent will make this move. I have looked 5 steps into the future. I have used a prediction horizon of 5. That is what one part of MPC. The other part of MPC is I played my move, opponent played his or her move. Next step, what do I do? Next step, I will repeat that process all over again. I won't repeat that process for only 4 moves. I will again repeat it for as many moves in future that I can use. Okay, why does Vishwanathan Anand play better than me? Because I can visualize only 3 or 4 moves into future. Vishwanathan Anand can visualize 35-40 moves into the future. He has a better model for the opponent than I have for the opponent. Okay, as a result of poorer model and lesser prediction horizon, my moves are poorer than Vishwanathan Anand's moves. If I were to only look at one step into the future, I'm doing PI controller. If I'm not even looking at one step into the future, I'm only doing a P controller. Or sorry, PD controller if I look at one step into the future, P controller if I don't even look at any step into the future, PID controller if I look at steps in the past, one step into the future and the current step. Okay, that's the closest analogy that I can give. But technically, reasonable analogy is what I showed over here. If you are used to the concept of optimization, then MPC is much more related to optimization. The simple question that the MPC asks is, what is the best set of control moves into the future by solving an optimization problem subject to the current information that we have. The current information comes from a controller. Optimization problem is solved by the optimizer. If you don't have the optimization background, then please skip what I just explained, the last half minute. Okay. Okay, so hopefully this, I mean, this is the the most straightforward way in which I can explain. I'm not sure if there is any other way that I can explain. But one thing is that MPC is not related to PI controller or PID controller. So kind of use that to get the concept of, okay, you need integrator. Use that to get the concept of this is feedback. Use that to get the concept of feed forward. But beyond that, leave aside PID, because that is going to limit your ability to learn MPC. Okay. I hope that kind of answers the question in a more coherent manner. So hopefully that would be something that would be useful for you. Yeah, if not, you can ask follow-up questions on the forum, and maybe the TAs might be able to answer. But it's kind of a different concept than PI PID. PI PID controller are based on frequency domain and based on what your current errors are. MPC is based on using a time domain model to predict the future, and it's an optimization base. So uh, it's a different concept, and therefore thinking in terms of PID can become confusing. So I would say that other than the fact that you need integral action in order to get rid of offset, you require a set point that may be tracked. This is the concept of feedback. Other than that, you may not want to bring in too many other concepts from PID that can potentially be confusing. Yep. Yeah. Good. Okay. So I think we'll close this session. So thank you everyone, and hopefully this was useful session. And again, week 7, 8, 9, and 10 will talk about the fundamentals of linear control theory. So definitely attend that. Uh, and if you got confused over the last 2 weeks, don't worry. Week number 7 is going to be reset. If last 2 3 weeks went really great for you, again week number 7 will be reset. So keep that week number 5 and 6 aside, 4 5 and 6 aside. Mind fresh, 7 8 9 10. Week number 11 10 and 12, we will mix the concept from 7 8 9 10 and week number 4 and 5, sorry, 5 and 6, in order to use state space MPC. State space MPC is what is used today by everyone also. Okay, not the step response MPC, but I use the step response MPC because it gives a very good intuitive feel behind MPC. Okay, so with that, I come to the end of this lecture. So thanks everyone for attending, and we will close this session now. Okay. Okay. Thanks and bye.